All right, so we're going to go ahead and take a look now at another rule from SD plus. And these rules that we're looking at right now, these are called replacement rules. So they say that whenever you see one sentence, you can write another because those sentences are logically equivalent to one another. So if we're using SD plus, anytime that we had a proof and we were working and we had not P or Q on a line, we could write if P then Q on any line underneath it by this replacement rule. And the reason that these replacement rules hold is because in the SD system, these are logically equivalent sentences. So remember, SD plus is not any more powerful of a system than SD is. It just allows you to make shortcuts. So you don't have to prove this equivalency every time that you want to go from one of these to the other and back and forth. But we're going to go ahead and we're going to take a look at how to prove this rule in, or prove this equivalency in SD. So this is a biconditional that we're trying to prove. So the way we start is by making two subderivations. We're going to go from the left to right, and then from right to left. So these tend to be very long derivations, so you kind of got to write small. All right, so here we're starting with an assumption for purposes of biconditional introduction. And we're trying to get a conditional. So because we're trying to derive a conditional, we're going to assume the antecedent and try to show that the consequent follows. So we're going to assume P for purposes of conditional introduction. And try to show that we can get Q. So how can we do that? Well, one way we might typically proceed here would be to assume not Q, but I don't think that's going to, and show that we get a contradiction, but I don't think it's going to work in this case because I don't see any way we can get a contradiction. But we do have this disjunction that we can work with. We have this disjunction not P or Q. So why don't we use disjunction elimination on that and assume each part of that in turn and show that either way Q follows. So I like to start with the easy side. If we assume Q, obviously we have Q. So we're going to assume Q for purposes of disjunction elimination. And on line 4, we're just going to reiterate Q. Now comes the side that's a little bit trickier. We're going to assume not P and try to show that Q follows. So think about this for a second and see if you can see how we're going to proceed here. So line 5 is not P for disjunction elimination, and we're trying to get this. We're trying to get Q. So now we have a contradiction here. We have P and not P. So remember, when we're trying to use a contradiction, you have to assume the opposite of what it is you're trying to get, and then reiterate the contradiction down into that subderivation. So we'll assume not Q so we can use negation elimination on it. And on lines 7 and 8, we'll just reiterate P and not P down into the subderivation. So that's reiterations line 2 and 5. And now we can, on line 9, we have Q by negation elimination lines 6 through 8. And on line 10 now we can close out this both of these subderivations. And on line 10 we have Q by disjunction elimination. We've shown that if not P then Q, and if Q then Q. So we have to cite line 1, the line of the original disjunction, and then the lines of the subderivations, 3 through 4 and 5 through 9, or 5 through 8. 5 through 9. So 1, 3 to 4, and 5 to 9, disjunction elimination. So in line 11, we're now able to close this subderivation off, and we're done with this direction of the proof. We've shown that if not P then P or Q, then if P then Q. And we did that by lines 2 through 10, conditional introduction. Okay, so now we're down here. We need to go from if P then Q to not P or Q. So this time we're trying to prove something that's not a conditional. It's not a biconditional or conditional. So kind of what we need to do here most likely is to assume the opposite of this and show that a contradiction is going to follow. So we need to open up a new subderivation. And we'll assume the opposite of what it is we're trying to prove for purposes of negation elimination. So what can we do now in order to get a derivation, in order to get a contradiction? Well, one thing that we can do is to try to either get P, if we can get not P or we can get Q, then we can just use disjunction introduction to get this, and then we have a contradiction, and we can close this out and use disjunction introduction. Or use negation elimination. Use negation elimination. So let's try this. Let's assume P. And we'll assume P for purposes of negation introduction. We'll try to show that P gets us into a contradiction. So if we have P, then we can get Q by conditional elimination. Lines 12 and 14. And now we can use disjunction introduction to get not P or Q. Line 16. So that's line 15, disjunction introduction. Now on line 17, we're going to reiterate this into here. So we have our contradiction. And now we have a contradiction. We're able to close this out and conclude that not P. By lines 14 through 17. Negation introduction. So what you can do now is essentially do the same thing we did inside of the subderivation, and we'll use disjunction introduction to get not P or Q. So that's just disjunction introduction on line 18. And now we're going to reiterate line 13 down into here, so we have a contradiction. So line 20 is reiteration on line 13. And now finally on line 21, we can close this subderivation out. We've shown that this assumption led to a contradiction, so we know that this negation can't be there, right? Because this formula with the negation sign led to a contradiction. So lines 13 to 20, negation elimination. And finally on line 22 now, so we're done with this subderivation. We've shown both directions of the equivalency. So line 1 through 11 and 12 through 21, biconditional introduction. And that establishes the equivalency of these sentences to back up or to justify that replacement rule that we have in the system SD+.